Hello. Today we'll be talking about the history of chemical engineering, more so about the Bhopal disaster. This presentation is being presented by me, Cole, Faith, and Juan. All right, let's get started. To start off, chemical engineering is one of the broadest and most in-demand disciplines. Engineers work in a variety of industries, including energy, mining, chemical production, food production, and water treatment. In fact, due to chemical engineering's broad nature, it is often times difficult to give it like a definition. And I'm sure you've found it difficult to explain what chemical engineering is to a friend. However, the processes used in the industry, such as evaporation and fermentation, have been known since the early civilizations, but they were only applied in batches and not like the continuous processes that we see today. It wasn't until 1878 when George E. Davis, an English chemical inspector visiting chemical works around the country, took note of a variety of techniques used and then he used them and compiled them into a 12 lecture series focusing on the basic principles of today's chemical engineering. By the 20th century, there was a demand for large-scale physical separation and synthesis processes that could continuously run with high efficiency, which was a problem that no other discipline was fit to solve. Examples of these include the need for nitrates with the Haber-Bosch process, as well as the demand for petroleum and mass production of goods overall. With these demands, chemical engineering grew more than ever. However, in the event where safety measures aren't followed and or shortcuts are taken, whereby ethical constraints are not being considered, chemical engineering processes can quickly turn into disaster. Large chemical processes oftentimes involve toxic and flammable gases, as well as operations that occur at extremely high temperatures. A mistake at a chemical plant can cause serious fatalities. Some of these disasters include the Three Mile Island disaster in 1979 and the very infamous Chernobyl incident in 1986, as well as Fukushima in 2011, and a whole host of oil spills in the upstream crude oil acquisition. Um, some examples are noted in here. However, one of the most dangerous chemical accidents ever recorded is the 1984 Bhopal gas tragedy in India, a disaster that cost thousands of lives and resulted in permanent impairment for those who survived.
The disaster that we will be looking at today is one of the worst in chemical engineering history and is a grave reminder to any aspiring chemical engineer about the importance of safety and ethical process design during their career. This disaster occurred in Bhopal between December 2nd and 3rd, 1984. To provide some background information, the Union Carbide Corporation in the United States established an autonomous division, Union Carbide India Limited, with a plant in Bhopal, which opened in 1969. This plant was designed as a sister plant to the one in West Virginia and made a pesticide used by farmers in the area. Originally, the factory would ship in the chemical methylisocyanate, also known as MIC, into the plant, which would then be refined into further chemicals and the pesticides needed, such as Sevin. But eventually, the Indian government granted the plant operators the ability to synthesize MIC in-house. This posed a major issue. Between 1975 and 1981, engineers from the plant in West Virginia conducted routine safety checks and repeatedly warned of the possibility of a runaway reaction, even before MIC was allowed to be synthesized, meaning that the plant was ill-equipped to make the chemical in-house. Furthermore, MIC's volatility further increased the chance of a runaway reaction, which is what occurred on the night of December 2nd, 1984. Originally, the plant stored MIC in a tank connected to a flare system to get rid of dangerous fumes, and a pump that sent the chemical to other reactors for further use, as you can see in Figure 2, which shows a tank of MIC, a pump that sends MIC to further derivatives, and the pipes PVH and RVVH with nitrogen being pumped in, and MIC going through there and through the flare system, which burns off any dangerous chemicals, preventing damage to the surrounding towns. The pipes of the plant were made of carbon steel, which contains a lot of iron and rusts in contact with oxygen. Furthermore, when in contact with rust, MIC polymerizes into a large compound known as a trimer, which builds up in the pipes over time and looks like a sort of gunk. To avoid this, the plant designers injected the pipes with inert nitrogen, preventing any of the above reactions, because when there's inert nitrogen, oxygen cannot rust the pipes, and since there's no rust, MIC will not polymerize. However, the pump in figure 2 would often fail, so the designers of the plant had to come up with a solution which was haphazard and unsafe. The new system involved using a vacuum system to vaporize the MIC and send it to the next steps through a bypass pipe. To create this vacuum, the inert nitrogen system had to be shut off and emptied, allowing oxygen to enter the pipes, causing the pipes to rust and causing the MIC to polymerize inside when the vacuum system was created to send it to the derivatives. As you can see in the figure below, the pipes with inert nitrogen go to the figure 5, which shows a pipe that is rusted, and then goes to figure 6, which shows MIC coming in and nitrogen coming in, and MIC flowing through those pipes, which has a yellow highlighted rusty pipe, which shows the trimer that's being formed. And then above that, you see the RVVH pipes and the PVH pipes being filled with water, which acts as a way to clean out the pipes. Normally, the plant operators would close the valve connected to the storage tank to the overall system and wash the pipes with water, as you can see above. But polymer also built up in that valve, so on the night of December 2nd, 1984, when a worker was sent to close the valve and send water through the system, it leaked into the storage tank and reacted exothermically with the MIC. This caused an increase in pressure and eventual burst, leaking a 20-ton cloud of the toxic gas into the surrounding town. So this slide shows the state of the plant in 1984. And the plant of course, as I said previously, the plant in Bhopal was never meant to synthesize MIC, but the Indian government approved the on-site synthesis in 1981 due to chemical and financial reasons. The plant was already at risk of having critical failure, and by December of 1984, the safety features of the plant were in critical condition. And as you can see below, there's more information I previously mentioned, and we'll be moving on to the next slide now. Using a new technique of process safety assessment called layers of protection analysis, or LOPA, we can assess the probability of failure at Bhopal. So first of all, LOPA makes two assumptions. First, to count as a layer of protection, a contingency must not be dependent on any other contingency, meaning that it is on its own. Second, it is assumed that no contingency is 100% reliable and is prone to failure. Since nearly every contingency at Bhopal was dependent upon the circulation pump that often failed, Bhopal's failure probability was 0.1. If each contingency were independent, this would have been much lower, as is seen on the slides. Here you can see that that probability with 12 layers of protection would have been 1 over 10 to the negative to the power of 14, which would have been an unfathomably small number. However, since these contingencies were not independent of each other, the probability was 0.1. And for reference, any system with a probability of failure above 1 over 10 to the power of 7 must be redesigned. So this system was clearly unsafe. As for the local outcomes, this disaster resulted in over 3,000 deaths and 200 to 300,000 ongoing injuries. As a result, India passed an Environmental Protection Act, and the approach to safety was revamped in the industry of chemical engineering forever.
The Bhopal disaster had a significant impact on chemical engineering. Prior to 1984, chemical process safety was not a major public concern. This changed following the aftermath of the disaster. Not only did the public lose confidence in the chemical industry, the industry itself began to question its capability in preventing major incidents. This realization led to various initiatives being enacted to change the way chemical process safety is practiced throughout the world. This presentation will focus on the regulatory initiatives within the United States. The Clean Air Act amendments were passed in 1990. The amendments include several specifications pertaining to chemical safety and regulation, including maximum achievable control technology requirements, health-based standards, and requirements for the prevention of catastrophic releases. The MACT requirements establish standards for 187 pollutants, which the EPA is required to revise at least every 8 years. Any pollutant anticipated to cause health and/or environmental harm is regulated. The goal is to achieve the maximum degree of reduction in emissions. Health-based standards involve further intervention by the EPA when there is a situation where significant residual risk of adverse health and environmental effects remain even after the implementation of MACT requirements. And the prevention of catastrophic releases is achieved by establishing an independent chemical safety and hazard investigation board. The purpose is to follow up on accidental releases, conduct studies, and overall reduce the risk of accidents. The CAAA also resulted in giving authority to the Occupational Health and Safety Administration, OSHA, and the EPA to regulate the industry. OSHA developed and enforced a standard known as Process Safety Management of Highly Hazardous Chemicals, also known as the PSM standard. This standard is aimed to govern process safety. It involves 14 parts that emphasize management hazards, all fundamental to operating a safe chemical process. The EPA created the Risk Management Program rule, which is aimed to protect workers and the surrounding communities from hazards related to the release of toxic chemicals. Each company is required to create an RPM, which will be updated every 5 years. It also requires that an emergency response plan is in place so that everyone in the area is notified in the event of an accidental release. The EPA also catalogs the reports of chemical releases and makes it available to the public via the Toxic Release Inventory. The data included in the image is of the pesticide and other agricultural chemical manufacturing sector. Included in the diagram are the top polluting companies, the total release in millions of pounds, and top 5 chemicals released to air and water. The Emergency Planning and Community Right to Know Act was passed by Congress in 1986. As the name suggests, the law enforces emergency preparedness and public disclosure of the use and accidental release of toxic chemicals. As part of emergency preparedness, the company must document which chemicals may be involved in an accident, have a plan in place to notify emergency responders in the event of an emergency, and include state governments in the process of planning. This has led to the formation of state emergency response commissions and local emergency planning committees. As part of public disclosure and community right to know, there is an established reporting requirements to ensure that the community has access to which chemicals are being used and how to protect themselves in case of an emergency. The law requires the use of material safety data sheets that include information about the chemicals and potential health and safety risks. These data sheets are required to be given to local emergency planners and are made available to the public.
In conclusion, progress has been made towards chemical process safety. There has been a measurable decrease in fatalities and other workplace injuries. For instance, the rate of workers' fatalities have declined by 78% and the number of workplace deaths by 62% from 1970 to 1995. However, there are a few key areas for improvement. For instance, developing a better way to measure the overall safety performance of the industry. In 1999, the National Chemical Safety Program was created to establish a rational measurement of the ongoing status of the national chemical safety. While it did improve the baseline of future comparison, it has many limitations. In order to continue moving towards improvement the overall chemical safety process, it is imperative that we can quantitatively measure the rate at which advancements are being made. Another area of improvement includes ensuring that we, as an industry, learn from these incidents going forward. Oftentimes, accidents are not really defined and are categorized in a safety pyramid diagram, as we can see here. The base of the pyramid includes accidents classified as a near miss, where no injuries actually result. The next level is classified as non-serious injuries, then serious injuries, and finally, fatalities due to the accidents. Deeper analysis of the incident case study have shown that many times the underlying causes of the incidents are the same. However, they are categorized differently due to external factors that cause the incident to end in an injury. For instance, a gas leak on a day when the wind speed and direction occur, such as the gas does not encounter an ignition source, will have a very different outcome from a gas leak on a day when those factors align, such as the gas does ignite and cause injury. While the cause of the gas leak was the same in both cases, the two incidents will be separate categories. In order to ensure that we learn from these events, a broader incident definition should be used. The definition should not merely include near misses, rather it should be expanded to also state other relevant factors. In doing so, there will be a statistically increase in the chance that a lesson will be learned for future incidents analysis. In the next page, we can also find our sources that we use for this presentation. And with this, we end the presentation. Thank you.